I'm excited to introduce the first set of speakers for the webinar series. So myself, the community and product lead for PyTorch Geometric, Matthias Fay, the founding member of PyG and Kumo, and Manan Shah, the founding engineer of PyG and Kumo. So let me quickly cover what we'll talk about. So I'll spend the first part of the session talking about graphs and graph neural networks and how you can properly perform deep learning on them to maximize the value of the data. Matthias is going to talk about PyG, which is the best open source framework for building GNNs. We'll share some best practices and challenges in using PyG. And then we'll finish off discussing Kumo, which is the fastest, easiest way to productionize GNNs at any scale. And we'll cover any algorithmic approaches and production tooling that can make you successful. So Manan will cover scale and orchestration. So now let's go into GNNs. So representation learning has been a key paradigm change that's had major advancements in the field of machine learning and deep learning. Deep learning evolved to have models designed to handle specific types of data, and these models learn the representations of the entities behind the data. So the most obvious example of this in the past has been convolutional neural networks, which are built to learn the representations of objects and physical features and structures behind the pixels. So as a result, these models have become super efficient at working with pixels. So certain layers will learn outlines of shapes, others will learn fine-grained features like noses, ears, eyes, and then the embeddings produced by them are very effective for their given use cases. So they're most optimal for the problem that you're solving. Because of this, you need much less examples and labels to train, and you end up with far superior model quality. Now, most data representing real-world applications and complex systems we feel are best described as a graph. A graph has nodes or entities and edges that can connect them. Now, these edges can be different relation types, they can be interactions, or they can combine them into parts of a structure. So some graphs are more obvious. So social graphs, which represent people, content, ads, posts as nodes and interactions between them as edges. Financial transactions, so payments between individuals, banks, companies, or communication networks. E-commerce and marketplace businesses that have buyers, sellers, and goods that are all connected in various ways. And then there are less obvious ones. So molecular structures, drug and disease pathways that combine and activate proteins that are useful for discovering new drugs. There are knowledge graphs where you can merge different entity types onto the same graph. Language models are also a graph, any kind of dynamic system that can be used for simulation, or any kind of traffic patterns such as trains, roads, or walkways, and many more. Now, graph neural networks try to combine these two concepts. So here, you're applying representational learning on graph data, the same way that convnets embed pixels and learn different representations on those images. GNNs will do the same for graphs. The embeddings capture information about how the entities relate with the rest of the graph. They'll capture topologies and hierarchical structures while also operating at a fine-grained level to understand nuanced features and direct relationships. GNNs are very flexible in their ability to operate across many different tasks and objectives. So GNNs generalize deep learning to graphs. Each node is effectively a computation graph where all the nodes are connected in various ways. And this gives you some signal about that node and gives you a strong representation of the entity as it relates to the rest of the graph. So the node is going to aggregate information from its neighbors using subneural networks, and the models will have strong inductive capability in looking at new nodes by making inferences from the rest of the network. So one of the key advantages for GNNs is the ability to adapt to complex data input. So you can think of GNNs as adapting to the data rather than trying to impose a set structure. Networks tend to have arbitrary size and topology. They don't really have a fixed ordering or reference point. So traditional ML, which typically expects a fixed ordering or sequence, isn't built in just this format. So what ends up happening is you impose a fixed ordering that is artificial in nature. GNNs, on the other hand, would capture an amorphous heterogeneous input, which is more indicative of real systems, which always have mixed inputs. For example, if you're an e-commerce platform, you might want to combine on the same graph things like click streams, event logs, images, annotations, text, hierarchical structures, and you can take advantage of input from each. Social network will want to combine users, content, pages, ads, all in the same graph. Content recommendation platforms might have visual images, topologies, text, and other features as well. GNNs are highly flexible and expressive models. So they'll take different network architectures and models and then combine the best of each depending on the use case. So you can think of CNNs and transformers as special cases or more of a general structure which is useful when each node has its own unique structure defined by that computation graph. So this leads to better performance at scale. So treating inputs as interconnected, you're able to aggregate and combine information that lets you detect complex relational patterns at scale. And this is really difficult to fully capture with manual feature encoding. And this results in learning representations of both the structure and fine-grained features. You can create powerful and flexible embeddings. So you can use these embeddings directly in existing models, or you can use them to power predictions for end use cases. So for all the reasons discussed in the previous slide, the embeddings are going to leverage information across the entire subgraph for any given node. So this will let you generalize really well to unseen or new nodes of the network where you don't have much historical data. So some examples of that might be when Spotify begins to recommend podcasts without having any podcast specific data. They'll leverage preferences from other pieces of content where they do have major data sources. Airbnb was able to identify recommendations for new hosts when a host joins the platform based on other nodes they're connected to. Now, we started seeing leading ML teams adopting GNNs because they drastically improve performance on most applications. So think of recommendation, personalization, fraud anomaly detection, forecasting, any kind of dynamic systems modeling. So for example, Pinterest built something called PinSage to enable representations of pins, which are concepts, and boards, which are collected pins, and then they embed those to significantly improve top-line metrics. So they were able to do this for the entire graph of content users, and they were able to see repin rate improve by 30% and impressions by 25%. Similarly, with personalized experiences with Uber and Spotify, they created very curated experiences. So Uber Eats will embed people, restaurants, and dishes into the same embedding space. And so they're able to, on the home screen, recommend really good places and items off of a menu for a person to look at right off the bat. Spotify curates the homepage so that your homepage is full on things that you would likely listen to. And like I mentioned before, they're able to recommend podcasts, which is the new content type for them to their users. And Amazon's fraud detection system has improved by 10x in catching bad actors. And they also use graphs and co-purchasing prediction, which has seen massive improvements of anywhere between 30 to 160%, depending on use case. Now, this brings us to PyG and Matthias. So without further ado, let me give Matthias the host privileges.
Okay.
All right, Matthias.
That works. Hope you can see my screen.
Yep.
Yeah, thanks for handing over, Ivailo, and thanks for everyone joining. Cool to see. So today I will be talking about PyG first, best practices and challenges. So let's dive in. So I guess most of you know what PyG is, but those for you that aren't familiar with that is that PyG, or Python Geometric, is a GNN library that tries to bundle the state-of-the-art in graph representation learning into a single library. And it does so by implementing like GNN layers and architectures and ready-to-be-used examples from latest research, and you can directly make use of that, extend it, and build your own pipelines. And it's also cool to see that it gained so much traction and popularity over the last year. So for example, we see that it's approximately used in like over 2K research papers up to date, which is just crazy to see. And I'm also very glad that we have now over like 350 contributors all over the world that try to make PyG better. What we also achieved in the last year was that we built a community and a team around PyG. So PyG is now actively maintained by different universities and companies, and I'm especially proud to see that Intel and NVIDIA are both really engaged in accelerating PyG, both for CPU and GPU. So at the core of PyG, we have like 4 different components, and at the heart of it, there is the component of graph-based neural network building blocks. And that means that PyG bundles message passing layers, normalization layers, pooling and readout layers, and so on. And they are all written based on a unified interface so that you can easily write your own on top of that. Next, we have like graph storage, data sets, and data loader routines, which means that PyG supports homogeneous graphs, heterogeneous graphs, temporal graphs, and so on. We now provide access to over 200 benchmarks data sets, which will be downloaded and processed by default and are basically ready to be used in any GNN pipeline. And there also exists different or variety of different data loaders or sampling techniques, such that you can easily choose the best sampling technique for your specific use case. Next, we have the concept of graph transformation and augmentations. And I feel that like kind of an unexplored building block right now, but I think it's important to highlight that the graph structure dictates how well your GNN can actually perform on a given graph. And so we provide options in order to improve the graph structure, like graph diffusion or metapath creation, to reach faraway tables much more easily. We also provide support, for example, for missing feature value imputation. And it's, I think, important to note that PyG is not only limited to graphs, but you can also transform measures or point clouds to graphs and then use message passing on top of that. So that works well as well. And lastly, we worked hard on making PyG a good starting place to get familiar with GNNs in a practical sense. And that means that we provide videos, call-up notebooks, a lot of blog posts recently. And I'm especially proud of these application-driven GraphML tutorials from Stanford, which like practically guide you on how to use PyG across different applications. And so I just want to give a quick overview of how PyG is usually used to get a working GNN. And I think it's important to note that PyG is designed to be highly modular. So all of these different steps in the pipeline are super exchangeable. So you can swap data sets, data loaders, and so on, and everything still hopefully should work out. And so the first step in the pipeline is that we usually need to take care of what is the graph we are actually working on. And so, as I mentioned earlier, you have access to benchmark data sets, but if you want to operate on your own graph, you need to create this graph, instantiate it, and attach the specific graph transformations to it. So what does that mean? So for graph creation in PyG, it's important to note that PyG expects a graph in a pre-processed form, so that it means that the graph should be already present in like COO or CSR space format, a sparse matrix format, sorry. And given that, it can then be used to model like complex heterogeneous graphs, as shown on the right, where we have like a heterogeneous graph with users and products, and these products and users are then connected to each other through a bipartite graph. Importantly, we are not only attaching the graph structure to the data object, but also a set of curated features, such as node features or edge features. We can add time information to it and so on. So the problem we often see here in GitHub discussions or in Slack discussions is that it's usually very convenient to work with benchmark data sets that are known in the academic setting, because these data sets are already curated and ready to be used. But if you're starting completely from scratch and just having your raw data, then it might be challenging to implement the PyG expected graph format from your own. And so what that means is that this involves challenges such as what is actually the best graph design I should choose for my given use case, because that graph design is strictly coupled to how message passing operates in GNNs. And then there are questions on what are the features I can use for my model. How shall I design node features and edge features and so on, and how should I select them? And then the third most important step is that you actually need to encode these features, like the raw data from these features should be converted into a format that is suitable to act as an input for neural networks. And that is usually like a continuous format. Afterwards, you actually have to take care of the task formulation that is strictly tied to the graph. And so in principle, PyG supports any graph-related machine learning task, but you still would be responsible for creating the training tables, training labels, and the splitting scheme. And as shown on the right, usually that works by just attaching some form of node label or graph label to the graph, and then doing some form of random node splitting or a random splitting of your set of graphs. In the academic scenario, then you usually don't have to take care of that because training labels and dataset splits are usually predefined, and that has a simple reason. That is that we want to have maximal reproducibility across research so that different models that build on top of each other actually work on the same input data, input labels, and input splits. But if you're working on your own data, then that actually means that you need to create your training labels and your data set splits from scratch. And so what that means is that you need to take care of how you can actually convert your raw training labels to map to an underlying machine learning task, such as binary node classification, link prediction, and so on. It's also important to note that if you're like in a temporal scenario, and that is often the case if we're working with graphs, then you need to achieve or need to take care of avoiding any data leakage, such as the label that you're trying to predict does not gain any information of how it was computed from the graph. And next, and I think that's a quite important topic, is that you need to think hard on how you want to split your data. So in most cases, people are using random splits, but these tend to be like overly optimistic and do not really reflect to like a pipeline that would be used in production. And so you need to think harder about how you can achieve a data set splitting that closely matches how you would apply your model or your GNN in real world applications. After you define your graph, the pipeline then continues to define how to obtain mini batches from this graph data set. And so there are different principles on how to do that. And the most common one is that you're working on a single large graph, but that single large graph is too large to fit into GPU memory. And so you're doing some form of sampling, like you're sampling subgraphs, and you only feed these subgraphs into the GNN as a form of mini batching. And so I'm happy to see that PyG provides over dozens of different sampling techniques, each with their own advantages and disadvantages, such as node-wise sampling, layer-wise sampling, subgraph-wise sampling, and so on. But there is like a real challenge to overcome if we think about large-scale real-world graphs that may not even fit into a single machine. And that basically means that you need to extend PyG to support these scenarios. That means that we need to move these data structures, these graphs, out of the core for independent scale out. And we achieved that in PyG through some form of abstractions known as feature store and graph store, but you would still be responsible to connect these feature stores and graph stores to your underlying backend. Then there are major challenges in optimizing this end-to-end throughput and this distributed pipeline, which means you would need to have a fast lookup of features and an efficient distributed graph storage that has no problems in sampling efficiently. If you've done that, then you can really leverage the full PyG functionality. And that means that you have full control over how you define your GNN, what are the building blocks you use, what are the layers that you may want to override and extend. And there exist multiple ways to do that. For example, you can use a predefined GNN model from PyG that is designed based on best practices known in the GNN community. You can use predefined layers and building blocks, and then just deal with how you connect these building blocks for your specific task. And then the third option would be that you completely ignore any predefined building blocks and just use the interfaces PyG provides to create new layers that are suitable for your given task. Afterwards, you leverage training and inference routines from PyTorch, which means iterating over your data, moving data to the GPU, running forward passes, computing losses, and then optimizing the model parameters based on backpropagation and gradient descent. The training process in PyG is like super general. It is fully customizable, both from like a model architecture standpoint and also from a training routine pipeline. But that also means that there are many flexibilities and challenges to overcome, because model architecture and training routines are like super task and data dependent. And so you may want to, it is unclear like what is the best GNN for your given machine learning task, because GNNs are usually designed with different properties. You may see issues in your graph that restricted from capture like long range information. And so you may think about how to enable reaching that information from nodes far away in your graph much more easily. You may see issues with overfitting, class imbalances, underfitting, and so on, and you would have to react adaptively. I think there's major challenges in how you actually tune the parameters of neighborhood sampling or of sampling in general, like how many hops do you actually need to sample to get meaningful signal in. If you're working in a temporal pipeline, it's also crucial to think about how to ensure that your model actually generalizes over time, such that you can actually use it in production. And if you see like heavy overfitting and so on, you might think of much more crazy architectures, such as self-supervision auxiliaries, pre-training to get better model parameter initializations, and so on. And so there are a lot of flexibilities here in order to train your GNN. And so what that actually means is that all of these challenges makes it very complicated to productionize GNNs. And so while PyG is a great library to enable GNN training and research on it, you actually still need to think hard about how to effectively map your industry graph to the given format of PyG. So you still have to deal with graph designing, feature engineering, designing custom GNN architectures for your specific problem. You have to deal with model training, evaluation, inference pipelines, and many, many more. And so a lot of these actually require GNN expertise. But it's not the end of the road. So if you really want to productionize that, then you may deal with such large graphs that it's tricky to use like an in-memory implementation for that. And so you have to find ways for an independent scale out, like connecting to graph databases, custom feature and graph store implementations. It's also tricky to think about that if your graph is temporal, so it's ever changing, then you actually need to manage the life cycle of your graph, updating it accordingly if you run new predictions. And then there are different DevOps requirements, such as secure data ingestion pipelines, or dealing with orchestration, such as retraining your model or scheduling inference calls and so on. And so that brings us basically to the Kumo Enterprise GNN platform, because the Kumo GNN platform has the goal to avoid all these issues by providing a platform that deals with everything previously mentioned. And not only does it deal with everything previously mentioned, but it also has a goal to be as efficient, as scalable as possible. And that potentially means scaling your GNN to over 50+ billion entities. And so the motivation of Kumo is that your enterprise is basically a graph. So if you're working on a relational database, that actually means you have entities in your graph that relate to each other. So you may think about like a commerce system, which has customers and items. And these customer and items are connected through each other through something like orders. If you're in a finance setting, then you may have accounts, and these accounts are related to transactions or loans and so on. And so these relations also describe how that can map to a graph. Social media is a classic example as well, where you have like users, you have their user profiles, their locations, their activities, their posts, their friendships, and so on. And this is actually an example of a very highly relational graph you can learn a lot from. But it's important to see that this is a graph on the schema level. So we often frame that as a meta graph. The actual real world graph is given at the level of individual records. So you could think about that each row or each entry in your database is actually a node in your graph. And these nodes are then connected through other nodes by primary key and foreign key relationships. And so the goal of the Kumo GNN platform is to make working on relational data as easy as possible. It is important to note that PyG is at the core, but Kumo is actually much, much more. It means that we have native connections to cloud data warehouses. You no longer have to deal with graph creation and all the issues that come with it. You just need to define your schema, and Kumo will take care of creating the graph. We have a declarative language to actually construct various machine learning tasks and then define how these tasks get mapped to a machine learning problem. We have super powerful GNN models, encoders, and aggregations that are actually designed for achieving stellar performance on databases. We have included AutoML strategies, which can basically achieve good performance in a featured manner. We have integrated explainability out of the box, and all of that comes with major promises to scalability. So we are able to scale to graphs with terabytes of data, all with secure protocols. And that also means that you're basically production ready within hours or days rather than weeks or months. So I quickly want to introduce you to the Kumo pipeline, and I want to do that in a practical sense. So we want to take a closer look at the H&M dataset. And the H&M dataset is a fashion dataset, so it contains of users and products, and it got really popular through the Kaggle competition, which has the major goal of recommending new products to users that the user will likely buy in the next 7 days. So we will have a separate webinar on recommender systems, link prediction, and ranking, and so on. So today, I want to showcase the H&M datasets on different tasks, especially churn and LTV. So what does that mean? The Kumo SDK basically provides a simple interface to register your meta graph or your database schema within your IDE. And all you need to do is instantiating a new Kumo graph. And given that graph, you can actually connect or add tables to it. So that means you could add a users table, a sales table, or a products table, and these all link to different data sources. Importantly, you can also add metadata to these tables, such as what is the primary key, what is the time column of a specific fact table, and so on. And then we provide an interface to link these tables together by using the concept of a column group. And that means all the foreign keys a table can point to. And that means, for example, the sales table has a foreign key called user ID, and that maps to the primary key of the users table. And the sales product ID is a foreign key, and that maps to the product's primary key of the products table. Afterwards, you can fully inspect your data, your graph linkage, and so on, right within your IDE. For example, you can query dataset statistics such as give me the number of rows for the users table, or give me the minimum timestamp that is present in the date column in the sales table. And that all feels kind of natural and Pythonic. And also, you can take a sneak peek at your data by, for example, querying the first rows of the products table, but only take a look at the ID column and the description column, and that all works right away. Afterwards, or after you create your graph, you now deal with the problem of how to formulate the underlying task you want to tackle. And as said before, today I want to take a closer look at churn, which could be defined as the likelihood of an active user to not buy any product in a certain amount of time. And here we set that to the next 90 days. And we actually developed a simple and declarative language to express this task quite easily. And this language is called predictive query. So it actually tries to query the future. And what that means is that we usually think about an entity we want to make predictions for, and then a target table from which we get the signal on what to predict. So in that case, we could formalize churn as a predictive query that tries to predict that there exists no sales event in the next 90 days, which is given by this interval 0 to 19. But we only want to predict on active users, which means we have a where clause that says that there needs to exist a sales event in the previous 90 days. And we actually want to predict that for each user in our user table. Kumo will then generate training labels from past data across multiple timestamps to train and evaluate a GNN across time. And that also means that you don't longer need to worry about any data leakage problems because Kumo will automatically handle any time correctness nightmares. And these are really nightmares, but it's working well. And also, Kumo will automatically determine the best training strategy. So there are actually multiple ways to train against a churn event, and Kumo will figure out the best way on how to do that. For example, you could treat churn as a binary classification problem, where you just have labels 0 and 1 if a user is active or not in the next period of time. But you can also be more crazy and train against something like time to next event, and then leverage the obtained distribution on how to determine if someone has churned or not in the next 3 months. The predictive query is actually a super general language to formalize different machine learning tasks. And it's quite natural to have multiple predictive queries defined on the same meta graph. So for example, you only need to instantiate your graph once, but then can query the future for different tasks on the same graph. And that means we can again predict like churn for active users, but we can also use that graph to predict like 7-day product affinity for all users, which means we find the best products a user will buy in the next 7 days. You can also leverage predictive query to predict something like 3 months LTV, which would map to the summation of all sales a user will do in the next 3 months. And you can also think about something like predicting price band preference, which means what is the average price a user spends on a given product or on all products in the next 90 days. These predictive queries will then get mapped to all kinds of different machine learning tasks. So for example, churn will get mapped to temporal node classification, for example, or product affinity will get mapped to a link prediction setting, and so on. In the SDK, that looks pretty straightforward then. So you have a predictive query object that you're initializing, and you connect these predictive query objects to a given predefined graph, as shown earlier. And then all you have to do is basically writing your query string as part of it, and Kumo will then take care of the rest. Next, I want to highlight what is then happening under the hood. So we now have our graph meta or meta graph definition. We have our predictive query definition. So we have basically everything to start training. And so the first step that Kumo does is that it materializes the graph. So it automatically generates a graph from the given schema, from the given data sources, and from the given predictive query. And it's really important to know that the structure of the graph has one of the most strongest impacts on model performance, because you want to ensure that it maps to the message passing paradigm of GNNs super closely. And what we find especially successful in Kumo is interpreting the Kumo graph as an hypergraph. And that means that all connections through these fact tables like transactions, sales, and so on actually describe a hyperedge, like a triplet of user, product, and transaction. And the hypergraph here means that we're actually learning a representation for each triplet and then distributing these representations back to each of the entities. Of course, we can think about optimizing that. So for example, if a transaction does not hold many features, you may want to collapse that into a many-to-many table, such that you're basically dropping that table. But that is only useful if in case the transaction table is not feature-rich. And if you're dealing with a lot of tables, and some of these tables are actually far away, so you need multiple hops to reach them, then we're leveraging MetaParse to get this information closer to the given entity. After materializing the graph, the next step would be to connecting the right labels in time to the given entity. So we have our predictive query, which for simplicity here maps to a binary node classification task. And then we connect each entity to a given label that is true at a certain point in time. And that basically looks as follows then. Afterwards, your graph is materialized, all your training labels are present in your graph. You now have the option to create your model. And there exists two options to do that. The first option is you use Kumo few-shot AutoML architecture and hyperparameter search. And that is designed to basically work out of the box on any data set and achieve satisfiable performance. So the principle here would be you define the query and simply press go and let Kumo work. If you want to explore more what is going on behind the scenes, you may have a machine learning background or some domain understanding of the business problem, then you can actually dig much deeper into the Kumo GNN and model plans and provide an effective GNN design space. So let me show what that means. So we now have our churn predictive query. And this predictive query can be inputted into an auto trainer object. And that auto trainer object holds all the different options and configurations to manipulate the desired outcome. So as an example, you would have full control over data split strategies and ratios, whether you want to upsample or downsampling different target classes and so on. You have full control about the metrics you want to evaluate on or you want to tune on. And you have full control over the training budget, which means like number of trials you want to run, the number of maximum epochs and so on and so on. But that is not the end of it. So we also provide major control about the model space and the design GNN design space. So as usual, you would tune something like dropout, activation, normalization, and so on. But the most important hyperparameter here, or the most interesting one, is probably the space of the neighborhood sampler, which determines what are the tables you can actually reach, what is the best strategy to sample temporal neighbors, and so on. So here you have full control about number of hops to sample, neighborhood sampling strategy, and so on. Next, I want to quickly talk about how we designed our GNN model to achieve stellar performance on the relational databases. And it's still important to note that GNNs shift the performance improvements from feature engineering to how we design the task and how we design the model. So we're not really doing feature engineering here, but instead we're finding better models that are more applicable to work on relational databases. And what that means is that a GNN on relational databases needs to fulfill two major important things. The first one is that it needs to treat time as a first-class concept, because time directly dictates which are the facts you aggregate, or the events you aggregate within your GNN, and how far away are they in the past, how do they relate to each other, and so on. And the next thing is that you need to have like a strong GNN that can both reason about the features in your graph, but also the graph structure. So for example, how popular is a given product? You naturally get that information through the node degree, for example, rather than a feature present in your graph. And so with that in mind, we can then think about what are the basic questions you may find useful to obtain good model performance and how you can actually achieve them. So for example, if you think about a GNN starting to sample neighbors from a user table and then reaching products and views in the first hop, then that would be information about which user has bought which product or how active was the user in the past. But then if you continue sampling and continue message passing on these subgraphs, then you get actually more broader information in. For example, information about users that have bought similar products, or how active users were that looked at similar products, and so on. So that is actually a super flexible design to not reason about feature engineering, but more about how we can design models that can capture these signals. And so the first step here is that we're actually separating our model into three components. And the first component is the encoder part. And this encoder part takes care of embedding the raw heterogeneous features into a single shared embedding space. And what I mean with raw heterogeneous features is that your table may contain numerical columns, and so you may encode them as raw values normalized. You may want to bin them into certain groups. You may want to combine different strategies, and so on. Your graphs may, or your table may hold categorical values, such as types, strings, and so on. And there exist actually multiple ways to encode them or how to process them. And one would be like a one-hot encoding of the categorical. And that might work well for categorical values with low cardinality. And if you're thinking about categorical values with higher cardinality, then something like shallow embeddings might be more useful, as it restricts the memory footprint of your model. And then you can also think about how you handle like categories with low occurrence. You may want to fuse them together into a single one so that you're actually avoiding overfitting on these rare categories. Text columns are a pretty heavy beast. So you could think about encoding titles and so on as a bag of words of features using glove embeddings and so on. But if you're thinking more about columns that actually contain descriptions of products and so on, then a transformer might be more useful. Date columns, as mentioned earlier, are super important to let the GNN reason about time. So it's actually also super important to actually capture the meaningful signal here. And that would be, how long was that event, or how far away is that event in the past? And did it happen in a certain seasonal feature, such as did it happen on a weekend? Did it happen on a Monday? Did it happen at the beginning of the month, and so on? And that are all features that are not really encoding time as relative or absolute values, but more see that as a seasonal feature. And then there exist other types of columns or semantic types, such as postal codes, and you want to encode that such that postal codes encode or still encode whether postal codes are nearby, geolocation, images, etc., but Kumo can handle all of that. And importantly, Kumo will choose a good set of default encoders and will actually also tune them as part of AutoML based on dataset characteristics. But it's important to note that you have still full control about how you want to have features encoded. And so, for example, if you want to customize how the amount table of the sales table gets encoded, then you can do that by just assigning a new encoder to it. And here we would use the normalized values of that column, where all the values which are not present in the column would be filled in with the average value. And in addition, we would use some form of bucketing or grouping to group certain values into certain bins, while NA values that are not present, would be moved into a separate bin. Next, I want to quickly highlight the two main concepts we use in our Kumo GNN, and that would be temporal consistency, which means that Kumo GNNs treat time as a first-class citizen. And so we have our materialized graph, and that graph stays static, which means that if we want to obtain mini badges from it, we actually need to prevent data leakage directly during neighborhood sampling. So given a seed node we want to start sampling from and a seed time for this event under consideration, we actually restrict our neighborhood sampler to only see entities and events available at the timestamp for which we are making a prediction. We then have different parameters and configurations to tune these temporal sampling strategies, such as uniform sampling over all past events, biased sampling that favors more recent events with higher probability, or something like just sample the last k events of this given table. And lastly, as I said earlier, it's really, really important to encode these relative and seasonal time information, and we actually do that as some form of positional encoding, so it's some form of cyclical features to let the GNN reason about that on its own. The next thing I wanted to point out is related to the usage of expressive aggregation, and that refers to the fact of using multiple aggregations, which we found super, super crucial in obtaining good model performance. And so here we utilize this concept, and this concept is actually known as being provably expressive to capture diverse neighborhood information. And it works by basically using multiple aggregators such as mean, max, standard deviation, and so on, and then scaling these outputs by node degree information. So you can actually reconstruct something like sum aggregation from it. Importantly, degree information is also a temporal feature, and so you need to respect that. If you use degree information as a static feature, then that actually means you can no longer train a Chern model because that would leak information about whether there exists already an event in the future or not. And the last thing I want to point out is in our Kumo GNN pipeline is the usage of model heads. So we have our encoders and GNNs. And these GNNs basically produce embeddings or representation of nodes that we want to make a prediction for. And so we can directly use these embeddings and input them into some form of model head. And in that case, that would be a classification head to obtain predictions for this given predictive query. But we also can just return the embeddings produced by the GNN. And you can use these embeddings to connect them to other applications to also improve their performance. And lastly, I want to highlight some results we obtained both from an LTV query and from a churn query. And we compared ourselves against like an analyst baseline, which refers to some heuristics we came up with to predict whether the amount spent by a user or whether the user will churn or not. We also compared ourselves to an XGBoost baseline, which would mean that we would need to flatten tables and aggregate information from other tables. And then XGBoost can operate on this flattened single table and treat each example as isolated. We replicated the graph stage model and used that within our Kumo pipeline. And then lastly, we have our own dedicated Kumo GNN model designed for operating on relational databases. And here we can see that both on the LTV and on the churn query, our Kumo GNN outperforms all other models by a large margin. And I think that's pretty cool to see. But what's more cooler is that you can actually have a better time to value. So for example, it takes a long time to write like graph sage model in PyG, construct training examples, construct your graph. And so that would be around 600 lines of code and 16 hours spent, or you can just use Kumo and obtain state-of-the-art results in less than 1 hour. Other customer highlights I want to quickly point out would be that we built a graph of around 100 of gigabyte, including cookies, devices, advertisers, publishers, users, and so on. And the goal was to generate high quality representations for each entity such that they can be used in certain other downstream machine learning models. And the impact that gave by using Kumo generated embeddings was that we were seeing an up to 0.3 AUC absolute improvement on 3 different machine learning tasks. Other than that, we approach the problem of increasing cross-sell opportunities across new categories. And we tackled that by building, again, a large scale containing over multiple hundreds of gigabytes of data, including users, stores, deliveries, and so on. And what we came up with was a predictive query to predict new category purchase affinity for each user. And just by using Kumo predictions, we saw a 50% lift in precision at top 5% of users over their internal data science baseline. With that, I'm finishing my talk here and will be handing over to Manan.
Sweet. Let me share my screen. Cool. Can folks see the screen? Take that as a yes. All right. So I guess in this section of the talk, we're going to turn a little bit more towards a discussion of how we scaled Kumo to operate on the customer data sets that Matthias just described. On this slide, we have a representation of Kumo's distributed architecture at a very high level. The dark blue box at the bottom represents your data store or warehouse, where the raw data that corresponds to your tables is stored. Kumo requires temporary access to this storage for both training and for batch prediction. The Kumo architecture for large-scale GNN training is built around a central orchestration engine with dynamic task queues that makes it horizontally scalable and capable of orchestrating concurrent execution of thousands of stateful workflows and activities. It has 3 primary parts as part of this workflow: the control plane, the data plane, and elastic compute clusters. The control plane, depicted in the top dark pink box, comprises of a set of microservices that hosts highly concurrent execution of lightweight, short-running tasks for business logic. As you can see in the diagram, this includes a metadata manager and security and access controls, along with the actual workflow orchestrator. The control plane also triggers and tracks workflow execution, manages and stores metadata, and stores state regarding job results. The data plane, depicted as the cache box in this diagram, defines a cache storage for data, metadata, states, and artifacts. The data plane is read from and written to from both the control plane and the elastic compute clusters. Finally, the focus of this talk is the elastic compute clusters that host long-running, compute-intensive workloads for a given query executed on the Kumo platform. These workloads include data ingestion and processing jobs, the construction of the internal graph representation that Kumo uses downstream, and our auto-scaled Kubernetes and Spark environments with their associated distributed and scalable feature and graph stores. With this setup, we're able to achieve on-demand scale up and down of our elastic compute clusters in minutes. In this talk, we'll focus on the execution of large-scale GNN training on our elastic compute clusters. In particular, we'll focus on the innovation and the techniques that Kumo uses to enable efficient learning of over 20 billion entities as part of its GNN pipeline. Let's begin by discussing why exactly scaling GNN models is such a difficult and challenging systems problem. As Matthias mentioned earlier in his presentation, real-world graphs and features don't easily fit into the memory of a compute node. Moreover, even under the rare condition that one can vertically scale a compute node, and by compute node here I mean a node with an accelerator that can be used for downstream GNN training, the forward-backward pass of the training. So even if you can find a node, a compute node that accommodates an enterprise graph and all of its features, doing so is often extremely expensive and prohibitive. And it runs into further restrictions when one considers improving throughput through techniques like data parallelism. When performing graph sampling, the sampled subgraph size is also usually quite variable, and depending on the out degree of the nodes that are sampled as part of the subgraph. Handling this variability while maintaining a high training throughput and supporting flexible graph sampling algorithms is a pretty challenging task as well. At Kumo, we have a production-ready and scalable graph neural network pipeline that is built upon an elastic, heterogeneous compute architecture. It delivers high throughput training and low latency inference on large-scale input data, and works at a scale of approximately tens of billions of nodes and over 100 billion edges. Our approach to address the outlined complexities with scaling graph machine learning functionally revolves around modularizing the training process. That means that we specifically separate out each component of the graph learning pipeline as an independently scalable service. Precisely, we choose to implement a combination of an in-memory graph store and an on-disk feature store to scale up graph learning at Kumo. You can see a sort of diagram for how we use the graph store, feature store, and the trainer, which is the compute node, at the right in this diagram. In this architecture, the graph store is purely responsible for graph sampling. The feature store handles feature fetching, and the trainer handles the forward-backward pass on each training data point. The in-memory graph store is optimized for fast access and random lookup of a node's neighbors in the graph. And the on-disk feature store is optimized for high data volume and high feature fetch throughput. The overall interaction between the three modularized components shown at right indicates that the compute node first sends root nodes and sample parameters to the graph store. The graph store then responds with the sampled subgraphs that correspond to the root nodes that we send to it. Then the compute node sends these sampled subgraph nodes over to the feature store for the feature store to perform lookup of the features that comprise that subgraph. Finally, the feature store responds with an overall sampled subgraph along with all of its features, which can then be used as a mini batch in the trainer node for forward-backward. This architecture allows us to independently scale out each component of our pipeline based on the data size and bottlenecks that we encounter. It is also a very cost-efficient method as each service can utilize instances that are specialized for that purpose. To be precise, our training node is a GPU instance with the memory needed to store the mini batches it is processing in each iteration. Our feature store is an instance with attached solid-state disks and high disk memory, and our graph store uses a memory-optimized instance for fast random access in compute node CPU DRAM. Along with this functionality, Kumo provides MLOps tooling, training orchestration, and model management to supplement the end-to-end ML workflow. We'll next dive a little bit deeper into each of the components that comprise this pipeline. Each of these components that comprise this overall end-to-end training pipeline. So first on the feature store. The Kumo feature store is a scalable, embedded, and persistent key value store that is optimized for read throughput. It is implemented as a service with low overhead for feature fetching and communication over remote procedure calls, or RPCs. The implementation of our feature store was guided by 3 key ideas. The first idea involves the communication protocol. We use protobuf and gRPC to communicate between the data server and the compute client as part of our interaction between the compute node and the feature store. Precisely, we store individual node features as protobufs on the feature store embedded storage. For folks familiar with TensorFlow examples, TensorFlow example features are usually defined as a list of individual feature messages, which contain the name of the feature and the associated value that corresponds to that feature's name. This representation, however, is not super storage friendly due to the duplication of names in that example and the lack of memory alignment for different features. To circumvent this issue, we implement a small optimization by defining a separate feature configuration file aside from the actual feature storage and storing features with the same type in a compacted array. This allows us to get memory benefits as well as serialization deserialization benefits as well. The second key idea involves columnar data storage and row-wise data storage. On the client side, our feature store receives features stored as protobufs in the row-wise feature representation. You can sort of see this in the left-hand side of the figure at bottom, where the server features in protobuf are all row-wise. Node type A, or node A, node B, and node C have features name, age, email, and salary, and these features are all aligned in a row format. However, in the compute node, these features need to be converted to a column-wise feature matrix so we can easily perform feature transformations applied on columns. The image on the bottom left and the right-hand side depicts this process. In particular, we choose arrow as our column-wise data format to benefit from its zero-copy design. To achieve this goal, we also carefully designed a strategy to handle null values as part of the zero-copy strategy. The final idea involves efficient ordering for throughput maximization within Kumo. We want to optimize the feature access performance in our feature store by improving data locality, so we can maximize the number of features that are accessed in one access call to the feature store. We adopt a simple idea within Kumo to reorder nodes in the feature store based on those nodes' neighbors in the graph store. For example, in the picture at the bottom right, we place triangle nodes accessed by the same circle neighbor as close as possible in the feature store, and we place square nodes accessed by the same triangle neighbors as close as possible. This optimization works very well for a lot of real-world applications and gives a significant improvement in throughput that we'll see in the next slide. Here, we have some brief benchmarks as to how our feature store optimizations enable both latency and throughput improvements at large scale. At left, you can see the improvements we get at latency of converting raw features to tensors that are used in the downstream model. We're able to 3x the speed of converting 100,000 nodes with the compacted representation, and additionally get some small boosts by handling null values in a special way to get zero-copy benefits as well. Furthermore, on the right, we can see that the locality optimized graph within the feature store can achieve a 2x throughput. And as a result of both of these optimizations, we're able to fully utilize the GPU during model training with an on-disk feature store. Next, we'll discuss the Kumo graph store. The graph store is a sampling optimized in-memory graph store that is optimized for fast random access of outgoing neighbors given an input node. It is implemented as a service with low overhead for independent scale-out from the feature store and compute node. Recall that sampling in graph neural networks produces a unique computational graph for the seed node that generates a sampled subgraph. You can see a depiction of some of these sampled subgraphs at the bottom of this slide, where each individual node color has its own unique subgraph that is used as the computation graph in the GNN forward and backward paths. In order to ensure that we are able to achieve maximum flexibility and model performance at training time, it's important for us to ensure that our graph store design is flexible and easily extensible. To this end, we implemented a graph store that leverages core PyG sampling optimized algorithms on heterogeneous graphs in CSR format. This enables us to get fast random access of nodes' outgoing neighbors, and also enables us to fully utilize some optimizations that our collaborators at Intel have worked on. This graph representation also allows us to significantly reduce our memory overhead overall while maintaining high performance. Sampling as a service further enables parallel execution of multiple training and inference workloads together, resulting in avoiding CPU stalls in the compute node and better training throughput end-to-end. The overall Kumo AutoML training pipeline puts together the feature store, the graph store, and the compute node to run multiple training jobs in parallel, with low resource requirements on the GPU nodes. In particular, our pipeline can be seen at right, where we heavily utilize the data reuse that is enabled by our feature store and graph store implementations. An AutoML searcher algorithm, leftmost in the diagram, forms the brain of our training pipeline and decides which configurations that the trainers will execute based on trainer past performance, current performance, and other relevant metrics. This searcher intelligently samples a custom GNN design within our Kumo-specific GNN design space to ensure that the optimal set of parameters are learned for any given task. The executing trainers are launched all in parallel on Kubernetes and independently communicate with the feature store and graph stores through a shared mini-batch fetcher, which generates mini-batches that the compute nodes subscribe to. The resulting pipeline is highly parallel, highly scalable, and saves orders of magnitudes of costs. It's also extremely flexible and enables new machine learning approaches to be integrated very tightly with minimal additional overhead. Each compute node additionally is auto-scaled on demand to support concurrent users and jobs, and make sure that our customers see as low cost as possible as part of the training pipeline. Finally, Kumo's graph learning pipeline provides benefits beyond a single AutoML run. Our platform enables users to define a graph once and share that graph representation across multiple models without any changes in a user's data pipeline. This allows for embedding reuse across multiple models that share the same graph and provides a seamless user experience when solving multiple problems on the same graph. Furthermore, Kumo automatically handles data versioning of tables in a customer's data warehouse and ensures that new data generated in upstream pipelines is automatically used during training and incorporated at prediction time. This means that you're always able to access the most up-to-date embeddings and features, even as your data changes underneath you. And if those data changes result in degraded model quality, Kumo will alert you as to this fact and allow you to retrain models or investigate further as to what's going wrong, perhaps with use of Kumo's explainability features as well. Overall, Kumo's graph learning pipeline enables orchestration, hardware management, and provides enterprise-grade SLAs all under the hood. It's efficient and cheap, and scales to large graph at enterprise scale with 20 billion plus nodes and over 100 billion edges. These are graphs that you can't simply put into the memory of a compute node and expect to train with any reasonable throughput. Finally, we work directly with the abstractions that most businesses care about, that is raw relational data, and Kumo manages the construction of a graph, the management of the graph, and updating of the graph as new features and data come in, all under the hood as well. So if you're thinking about scaling your GNN training or thinking about how you might apply graph learning to your particular use case, talk to us. I'm sure we'll have a lot to chat about. And I'll pass it back to Avilo now for any final closing thoughts.
Awesome. So our parting thoughts here, as you've seen in the first part, most applications that you work on are likely best treated as graphs. So there's an inherent structure to the data that can be modeled using interactions and relationships. And when you apply tabular machine learning approaches, the traditional way will force your data into fixed rows and sequences. The problem with doing this is you're fundamentally forcing the data to fit into a new structure that causes a loss of information. So what you get is a loss of signal. And as you've seen with traditional pipelines, you end up getting a much longer iteration cycle and also worse model quality, which can then result in missed business opportunities. So when you're working on research applications, PyG is the best framework for building GNNs. You get to leverage the state of the art and access the best GNN models and architectures and have fully customizable GNN building blocks. Now, when you want to deploy to production, Kumo is the best all-around approach based on time to value, efficiency, and scalability, and having access to orchestration and all the right production tooling. And as you've seen from Matthias's talk, the right GNN approaches to fully maximize from your use case. And so with that, thank you guys for joining us today. A couple quick things here. We're going to publish the recording and slide deck. I know folks have been asking for this. So we're going to publish them on the website, and all the people who are registered are going to get an email on where to find them. And we're also going to continue answering any questions on the PyG Slack channel. So if you have any specific questions on anything that you've heard from myself, Matthias, and Manon talk about, feel free to ask there. And just a quick point is we'll have more of these webinars and workshops coming up. So they'll focus on different areas of graph learning. So some of them will be more around just understanding how graph learning tackles specific use cases. So the next one that we have coming up will be link prediction for recommender systems. So we'll discuss the recipe for building and designing a recommendation engine using link prediction, specifically around ranking. And so we'll incorporate industry guest speakers and we'll talk about best practices and challenges as well. So with that, thank you guys so much, and hopefully see you guys next time. Thanks, everyone.